So let's get into an example here. We aren't quite ready to talk about reactions at equilibrium yet. We're getting a little bit ahead of ourselves, but we can't talk about this next part without briefly explaining what it means when a reaction has equilibrium. Now, most chemical reactions actually are happening forward and reverse at the same time. Not all, but most. What that means is that every reaction that happens in one direction can actually happen in the opposite direction. Take, for example, this, where you take heat and H2O and CO2 and you create this substance and oxygen out of it. But this reaction could take these two as the reactants and create these as product. So the way that the reaction is written is meaningful. If it's written like this, these are still the reactants on the left and the products on the right, but we say that this reaction is reversible. So now our arrow is actually double-sided, which shows a situation at equilibrium. Now take a look at this reaction. Which direction is spontaneous? If I take the heat, the water, and the carbon dioxide and go to the right, I get this and oxygen. But if I take this fuel and combine it with oxygen and actually spark, this reaction would go in this direction, releasing heat. So basically what I have here is a combustion reaction written in reverse, where we've got fuel and oxygen, and we all know that combustion reactions happen spontaneously. Once you start it with a little spark, it produces some heat and gives off carbon dioxide and water, and this reaction is spontaneous. So looking at a reaction, you can kind of get some ideas whether or not the reaction is likely to happen spontaneously or not, in which direction, based on your everyday experience as a person living on Earth. This reaction is actually spontaneous going back to the left because we know from our own experience that things that combust do so spontaneously. But water and carbon dioxide, along with a little bit of heat or a little bit of energy, can actually be used to force this reaction back to the right, although it's not spontaneous. Because if it's spontaneous to the left, it's not spontaneous to the right. But plants are doing this all the time. This is what plants do. It takes energy from the sun, some water from the ground, and carbon dioxide in the air, and uses that to force the reaction back to the right in a non-spontaneous way to make fuel, which it stores in its roots, and releases oxygen gas. And thank goodness they do that. Otherwise, we, as aerobic respirators, would not exist. And so reactions can be made spontaneous by changing the temperature, the pressure, or other variables, such as sunlight, like in this case, photosynthesis. And this brings me to my last point about free energy and spontaneity. And it has to do with exothermic reactions and endothermic reactions. Most of our examples of reactions that we know that happen spontaneously are exothermic. Like this one up here going to the left. It releases energy. If you rewrite this, then the heat would be on the product side, and then that would be exothermic. So we're looking at it kind of in reverse. But most of the examples that you know that are spontaneous are exothermic. So does that mean exothermic reactions are always spontaneous, and that means endothermic are always non-spontaneous? Well, that's not entirely the case. There are, in fact, a number of reactions that are endothermic, which absorb energy, which are spontaneous. Take, for example, an ice cube sitting on a warm countertop. It is absorbing energy, but is doing so spontaneously, and it is melting. And so there must be something else that is contributing to the spontaneity of the situation, of the free energy. Think spontaneous, think free energy. Exothermic does not mean spontaneous always. Most of the time it does. I agree with you. 75% to 90% of the time an exothermic reaction is spontaneous, but that doesn't always mean the case. And there are some examples where endothermic are also spontaneous. There must be a second thing to contribute to the free energy, and that thing is called entropy. Entropy is defined as the disorder of a system. We identify entropy with variable capital S. I don't know why it's capital S, but it is capital S. Now, it might seem strange to you that we're talking about things being ordered or disordered, and also talking about things either releasing energy or absorbing energy, and those two things don't seem to make sense with one another. But in fact, they certainly do. And we're going to talk more about their relationship on a later video. So it may seem at this point that I'm taking a huge turn from what we were just talking about, but I promise you that we'll bring it all back together here in a little while. Now, first of all, we need to talk about a fundamental law of the universe. And that fundamental law of the universe is actually one of our laws of thermodynamics. But that law says that the natural tendency of molecules is to move towards increased entropy. In other words, the universe is always becoming more disordered. Take, for example, a number of things over here. If you take a sample of gas, which is represented by these 9 dots, and you compress it into a tank, and then you release the gas into the room, those gas particles aren't just going to stay clumped up here in the corner. Over time, they will randomly disperse throughout the entire space. This is a state of more ordered, over here on the right, where this is a state of less ordered, or increased entropy. More disorder means increased entropy. If you take a ton of bricks and toss them off the back, you're not likely going to stack them up. It's not going to form a specific order. If you just throw them off one at a time without really trying, just randomly toss them off, it'll probably look more like a crumpled pile. This situation on the left is an ordered state, or less entropy, and this state on the right is disordered, or increased entropy. I also like to think of it as like washing your clothes and putting them in the dryer. When you're done, you take the clothes out of the dryer and you just throw them up in the air, and if they randomly fall down and they're all completely folded, well, that is obviously never going to happen, which is another example of why the universe is always trending towards more disorder. So disorder is just a natural thing. Think of your bedroom. If you don't take time and effort to keeping things neat and tidy, it's going to become more disheveled. It's going to become more random. There'll be books over here and plates of food under here, and your desk is going to be scattered with pens, pencils, iPads, cell phone chargers everywhere. Your bedroom is always working towards more disorder. You have to put in work in order to make it more ordered. And so entropy is another thing that contributes to free energy. It may not seem like it, but it certainly does. So the two things that tend to favor more spontaneous is an exothermic situation or a situation in which entropy is increasing. And both of those can be combined to calculate or to determine the free energy of a system. Free energy is not just a concept, it's a calculation. But before we can get to the calculation, we need to talk a little bit more about examples in the natural world in which entropy is increasing or decreasing. And there's a couple of clues to look for when you're trying to determine whether or not entropy is increasing or decreasing, because sometimes it's not as obvious as looking at a pile of bricks on the ground and go, yep, there's increased entropy, or a stack of folded clothes and go, entropy is decreasing in this situation. In chemical or physical processes, there's certain things that we look for, some clues as to whether or not entropy is increasing or decreasing. Reminder, entropy means more disorder. And so when you're looking at changing states of matter, gas is the most disordered, where liquid is more ordered and solid is the most ordered. So if you are converting from gas to liquid to solid, you are decreasing in entropy, or if you're going from solid to liquid to gas, you are increasing in entropy, and gas is the most entropic of the states of matter. So if you're changing state of matter, gas is high, solid is low entropy. Next, we'll take a look at situations that result in more particles. So if you have a large chunk of something and you crush it up into smaller particles, well, you are increasing entropy. This also includes dissolving, because dissolving is nothing more than simply crushing up the particles and mixing them with water. Now, this next one that we're going to talk about, you have to look closely at the reaction in order to see whether or not entropy is increasing or decreasing. And in a chemical reaction, as it's written from left to right, if you have more moles of product form than you do of reactant, then you are increasing entropy. And if you have more moles of reactant than product, then you are decreasing entropy. So here I have a little ratio. I have 2 moles of reactant compared to 3 moles of product. So in this case, entropy is increasing. Another example of entropy increasing is anytime something is at a higher temperature. The particles are moving faster, usually due to thermal expansion. They occupy a higher volume as well. And so because things that are higher temperature usually considered more entropy. If any of these are a little bit confusing to you, there's one general rule that you can hitch your wagon to, and it's that as a system becomes less organized, entropy increases. So hopefully, with these examples, you have an idea of what makes something more entropy or less entropy. And that takes care of this video lesson. Thanks for watching.